Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Fbise from Department of Physics. Hope you are all fine. Today we are starting new chapter. This is second chapter of second year, chapter 12, current electricity. Before starting the second chapter, let we take a review of previous chapter, that was chapter 11, electrostatics. In the previous chapter, students, we discussed in detail Coulomb's law, electric field and its intensity, applications of electrostatics, electric flux, Gauss's law and its application, electric potential, potential gradient, capacitor. We discussed in detail. Now we come to current electricity. This is chapter 12. After listening to today's lecture, you would be able to introduce current electricity, study current, drift velocity in conductors, electroencephalogram, that is EEG. Okay, let me start. As we all know, the definition of current electricity. It is the study of charges in motion. Unlike in electrostatics, we deal only with the charges at rest. Now in this chapter, we will discuss the behavior, the properties of charges when they are in motion. Electricity is easy to distribute. Authorities use high voltage transmission lines and transformers to distribute electricity to homes and industries. Voltages can be as high as 5 into 10 raised to the power 5 volts from power station, but by the time it reaches homes, the electricity has been transformed to only 220 volts in Pakistan. It is economical to generate electric power at a steady rate. Some of the most notable uses of electricity on daily basis are: it is used in entertainment, in many devices, in healthcare, hospitals, engineering in our industries, transport and communication, outdoors, household, commercial, offices, fuel, and space. Because I told you that current electricity deals with the charges in motion. So definitely we have to deal with the circuit diagrams. The circuit diagram is actually a closed path for the motion of charges along with the charges move. So when we deal with the circuit diagram, definitely we deal with the components of circuit. And when we deal with the components of circuit, we should be familiar. In the circuit diagram, when we have such a continuous line in the first box, it deals with wire. And wire stands for the paths for electricity to flow. For battery symbol, you can see the two bars, one is big, stands for positive terminal, the smaller stands for negative terminal. It pushes electricity through circuit. This battery pushes electricity to move through the circuit. And in the third box we have light bulb, this is the symbol, and the light bulbs, when it lights up, it resists electricity. When it glows, it means it resists electricity. Switch, we are having two options. Switch may be on, it may be off. And the last box, this is a resistor, and this is a symbol of a resistor, resist flow of electricity. This is for your information. We are having this eel. The electric eel is an electric fish which is capable of generating electric shocks of up to 600 volts. It uses electric shocks for hunting and self-defense. Now we come to steady current. Let me consider here a circuit diagram. What are the components in the circuit diagram? This is a length of a wire. The length of the wire, a segment of a wire is given, and L is the length of this segment of wire, and the two ends of the wire are connected with the terminals of the battery. The battery is providing a potential difference of V volt, and when the terminals are connected with the terminals of the wire is connected with the terminals of the battery, then there is a steady flow of current, that is I. The continuous flow of free electrons is called steady current. The conductor has a large number of free electrons. When voltage is applied, then free electrons, they will start moving towards positive terminal around the circuit as shown in the given figure. You can see the direction of flow of current from positive terminal of the battery towards the negative terminal of the battery. This directed flow of electron is called electric or electronic current. Current is due to flow of electrons, and electrons are constituents of matter. When we come to the components of matter, we know the nucleons, that is protons and neutrons, and electrons, these are negatively charged particles, they are revolving around the nucleus. Therefore, electric current is matter or free electrons in motion. The actual direction of current is from negative terminal to the positive terminal throughout the circuit. Why? Because when we deal with electrons, electrons are negatively charged particles, and when electrons move, it means negative terminal to positive terminal they move. However, in electron theory, it was assumed that that current flows from positive to the negative terminal of the cell through the circuit. This assumed direction is called conventional current. So it means here we have divided electric current into two categories. The first one is the electronic current, which is due to the motion of electrons, and the other one is conventional current. It is due to the motion of positive charges. Substances which have large number of free electrons will permit current flows easily and are called conductors. For example, copper, zinc, silver, aluminum, these are all conductors. In different current carrying materials, the charges on the moving particles may be positive or negative. In metals, the moving charges are always electrons. These are negatively charged particles. In gases, the moving charges are negative and it may be positive. These are negative and positive ions. In semiconductors materials such as germanium and silicon, conduction is partly by electrons and partly by motion of vacancies, which are known as holes. Holes are sites of missing electrons. It means whenever electron leaves its position, then leaving behind a vacancy, and that vacancy is known as a hole, and it is treated as a positive particle and act like positive charges. Current through the cross-section area A is the net charge flowing through the area per unit time. If a net charge capital Q flows through an area of conductor in time t, the current capital I is given by this equation 1, that is I is equal to Q over T. It means equation number 1 is giving you a mathematical definition of electric current. It means rate of flow of charge is known as electric current. The charge Q is measured in coulombs and time is measured in second. So the unit of electric current will be coulomb per second, and this coulomb per second is read as ampere and its symbol is capital A. 1 ampere is the current when 1 coulomb of charge flows across any cross section of a conductor in 1 second. Some multiples of amperes are 1 milliampere, which is equal to 1 small m A. Small m here stands for milli. 1 microampere is equal to 1 ampere. Now we come to drift velocity. What is drift velocity? Let me consider here a part of a conducting wire. In a conductor, however, there are a number of valence electrons and they are in the state of random motion. These electrons are free to move through the lattice of positive ions in the conductor. Such valence electrons in a conductor are called the electrons or conduction electrons, as shown in the given figure you can see here. The free electrons in a conductor are always in a continuous random motion. This random motion of the free electrons is due to thermal energy of the conductor, because the velocity of free electrons due to thermal energy of the conductor is termed as its thermal velocity, and it is usually represented by V. Furthermore, the number of free electrons in a conductor is given by N. Due to their random motion, the free electrons keep on suffering collisions with the positive ions in the conductor so frequently that the net flow of electrons in the particular direction is zero, because all of them, the motion of all of them, they are cancelling the effect of each other, resulting zero velocity. So if we consider here u1 bar, u2 bar, so on up to un bar, these are the thermal velocities of n number of electrons in a conductor, then their average thermal velocity would be equal to 0. Why? Because these velocities are equal in magnitude but opposite in direction. So overall they are cancelling the effect of each other. So the velocity, the net effect is equal to 0. So due to this it remains neutral. However, when some potential difference is applied across the ends of a conductor, you can see when we connect the two ends of the wire with the terminals of the battery, one with the positive, other with the negative, then there is an electric field E which is set up, and that direct from positive to negative N, and mathematically it is given by E is equal to V by L. If you remember, in electrostatics we have got this relation E is equal to delta V over delta R, and here R is replaced by the length of the conducting wire, that is L. So the direction of the field is from positive to negative. But we all know that in case of conductor there are free electrons. And what is the free electron? It is a negatively charged particle. So the direction of the electric field which is set up by these electrons would be opposite to the direction of the electric field which is set up by the battery. So these two are opposite in direction, and due to this the acceleration is given by this relation 4 A is equal to minus E over 1. Now the drift velocity, as we discussed in detail in the previous case, let me consider again the same segment length of a wire, capital L. The cross-sectional area is AA, and the direction of the electrons which are moving randomly are shown by the arrowheads. Every metal has a large number of free electrons which are moving randomly within the conductor. During this random motion, the free electrons collide with the atoms of conductor again and again, and after each collision, their direction of motion changes. Because of these collisions, due to random motion of all free electrons, there is no net flow of charges in any particular direction. Consequently, no current is established in the conductor. As I told you in the previous case, I showed you a video, and in the video I told you that the average velocity for the electrons is 0. So it means no current is established in the conductor. When the potential difference is applied across the ends of a conductor, then what happens? It sets up an electric field E at every point within the wire. The electrons experience a force in a direction opposite to the direction of electric field E. As a result of this force and the continuous collision with the atoms, the electrons acquire a net velocity which is known as a drift velocity. Drift velocity is basically a net velocity. The average velocity with which free electrons get drifted in a metallic conductor under the influence of electric field is called drift velocity. Symbolically, it is represented by V as a subscript small d. The drift velocity of free electrons is of the order of 10 raised to the power 5 meter per second. Now we come to electroencephalogram. It is a neurological test that uses an electronic monitoring device to measure and record electrical activity in the brain. It is EEG. Special sensors, which are known as electrodes, are attached to head and hooked by wires to a computer. EEG measures voltage fluctuations, that is, variations up and down, resulting from ionic current flows within the neurons of the brain. The brain's electrical charge is maintained by billions of neutrons. You can see here, this is electroencephalogram EEG test, and the first three stands for normal beats and the last one is giving you in a sleepy mode, that is abnormal behavior of brain. Neutrons are electrical charge by membrane transport proteins that pump ions across their membrane. Brain electrical current consists mostly of sodium, potassium, calcium, and chlorine ions that are pumped through the channels in our neutron membranes. The computer records brain's electrical activity on the screen or on the paper as wavy lines, and these wavy lines are giving you a graph, a type of graph consisting of wavy lines up and down. Thus, potential difference created by the electrical activity of the brain is used for diagnosing abnormal behavior. Here is a solved example, that is the first example of the chapter. Each second, that is 10 raised to the power 18 electrons flow from right to left across a cross-section of a wire attached to the two terminals of a battery. A part, calculate the current in the wire, and B part, in which direction the current is flowing. We are going to find it. For this purpose, let we come to the data given, and in the data given, we write down T, which is equal to 1 second, and that is giving you the number of particles, that is number of electrons, that is small n is equal to 10 raised to the power 18 particles, and because electron is an elementary particle, so E is equal to, small e is equal to 1.6 into 10 raised to the power minus 19 coulombs. And what is required? According to A part, we have to find the current, that is what is required? I. We have to find I. Now we come to the solution of this numerical problem. The formula we are going to utilize here is I is equal to Q by T. Alright, but here if you remember the previous lectures, we are familiar with the equation for quantization of charge. Capital Q is equal to N into E, where E stands for charge of an elementary particle, N is the number of particles. So in this way, we get here I is equal to Ne over T after putting the values of small n, E and T, what we get? We get here the magnitude of the current, that is A, that is I is equal to 160 milliampere. The current is flowing from left to right, that is in opposite direction of electron flow. The ability to observe without evaluating is the highest form of intelligence. Thank you, girls.